Hey everybody, and welcome to Chapter 18, Free Energy and Thermodynamics. We're jumping ahead to Chapter 18 to incorporate in our Chapter 9 discussion of thermodynamics a little bit more about other aspects of energy changes. Now, these are going to include other thermodynamic state functions in this chapter. Just to remind us a little bit of what we did in Chapter 9, thermodynamics is that initial and final state idea. We do not care the pathway, the in between steps, if you will, as to understanding the thermodynamics of a reaction. Thermodynamics is specifically looking at the initial and the final states of a reaction. Kinetics, on the other hand, which we will be discussing in chapter 14, is the intermediate states. So right now we are sticking with thermodynamics, beginning and end. What does thermodynamics and spontaneity have to do with anything? Thermodynamics will predict whether a process will occur under given conditions. Processes that occur in real life under specific conditions are called spontaneous processes. Non-spontaneous processes will require more energy input to actually go. So spontaneity is determined by comparing the chemical potential energy of the system before and after the reaction. Again, initial and final states. So if the system after the reaction has less potential energy than the system before the reaction is said to be thermodynamically favorable. That means that we are overall lowering the potential energy of the system, and therefore things are becoming more stable. The general idea here is that if a system can become more stable, have less potential energy, it will want to do so by itself. Spontaneous. Now, spontaneous does not mean fast or slow. A spontaneous process like combustion goes very rapidly. A spontaneous process like carbon in its diamond form going to carbon in its graphite form is a very, very slow process. But yes, both of those are spontaneous. They naturally occur. Spontaneous does not mean that it happens fast. A lot of people link these two together, and that is a big problem. Fast or slow is going to be dealt with when we talk about kinetics. Spontaneous and non-spontaneous is thermodynamics. Do not mix these two up. They are very, very important to understand the overall reaction. However, they are not linked together. Yes, my diamond ring that my husband gave me many, many years ago will eventually turn into a pencil. I've said this before, but it will happen over a very, very long time. So I'm not too upset. Any spontaneous process is irreversible because if the forward process is spontaneous, the reverse process will be non-spontaneous. So the reaction only wants to proceed in one direction. A reversible process is one that will go back and forth between reactants and products. This is called equilibrium. We will talk about equilibrium a little bit at the end of this chapter, and we will talk about equilibrium a lot more in chapter 15, but that's not until unit 4. So we're going to stick with our reversible processes, the irreversible processes, and say that if a process is spontaneous in one direction, it must be non-spontaneous in the other direction. So just like rusting of a nice old-timey car is a spontaneous process, we are going to assume that it can't go backwards. It's non-spontaneous to go back to its shiny form from the 20s. Spontaneous processes occur because they release energy from the system. Most spontaneous processes proceed from a system of high potential energy to low potential energy. These are exothermic. That is, again, referring to delta H specifically, but there are some spontaneous processes that proceed from a system of low potential energy to high potential energy. The delta H is endothermic, And that's because there is another factor affecting spontaneity. It's not just enthalpy. Enthalpy is important. Delta H is one of the factors that we are going to be looking at in this chapter. However, entropy is also a change that we have to observe. Enthalpy, just as a reminder, enthalpy, delta H, is the difference between the sum of the internal energy and the PV work, the pressure volume work, for the energy of the reactants and products. Entropy, on the other hand, is called delta S. And delta S is the difference between the randomness of the reactants and that of the products. Randomness, options, microstates. That's what we're going to be able to talk about. Let's just review enthalpy a little bit more to make sure we understand the two differences here. We dealt with entropy, enthalpy a lot. Delta H was everything that we just did in chapter 9. So let's just overarchingly identify what's happening here. Enthalpy changes, delta H, is generally measured in kilojoules per mole. And the reaction is generally exothermic if the bonds in the products are stronger than those of the reactants. Stronger bonds, more stable molecules. Exothermic because energy is released and delta H is negative. Other option, if the reaction is endothermic, it's because the bonds in the products are weaker than the bonds in the reactants. Endothermic, energy is absorbed by the reaction, delta H is positive. Typically, all right, enthalpy change is favorable for exothermic reactions. Typically, we like exothermic reactions, all right, because it adds to the idea that energy is released. Our products are more stable. Not always the case, but important to understand when are we favorable. Exothermic. Delta H, negative. Entropy, on the other hand, is a thermodynamic function that increases as the number of energetically equivalent ways of arranging the components increases. If your molecules have more options, and we'll talk about what options mean, if we have more options, entropy is favorable. Entropy is increasing. We like options. How many people like to go to Starbucks and just get a plain black coffee? No, you like the options. Maybe I'll get a mocha today. Maybe I'll get a cappuccino. Maybe I'll get a caramel latte. Options are great. And that's what entropy is deciding. Do we have options for rotations? Options for organization of our molecules? The more options we have, the more entropy we have, and the more favorable the system is. And that is because random systems require less energy than ordered systems. Now, entropy can be calculated using the Boltzmann equation we see here. We won't be using this one as much. It talks about the number of energetically equivalent ways a system can exist. We are mainly going to be qualifying entropy, the sign, as either positive or negative, which we will discuss in just a minute, or we will be looking at standard entropy states. Now, examples of entropy: salt dissolving in water. Entropy is increasing. When entropy increases, that is a delta S that is positive. All right, this is energetically favorable. Why is it favorable here? Because it means that there are more options for the energy distribution. I have heard this term as less ordered or more disordered. I don't really like this idea. I like the idea of randomness and options. All right, so when we take NaCl, something that is very structured, and we end up mixing it in water, there are more particles, right? We can think about NaCl solid going to Na+1 aqueous, and Cl-1 aqueous. There are more products than reactants because there's 2 versus 1, right? There are 2 physical ions in the products rather than 1 held together ionic compound. More entropy. So if the products have more particles than the original reactants, energetically, entropically, is favorable. Delta S is positive. If the reverse occurs, if we have more particles on the reactant side than the product side, then entropically we are unfavorable. We are getting more ordered, more structured, and so delta S would be negative. Let's look at state changes. Evaporation of water liquid to water vapor. When we think about this reaction down here, we are thinking about H2O liquid going to H2O gas. There's nothing different here about the balanced reaction in terms of the number of particles. H2O is not an ionic compound. All we're doing here is a state change, solid liquid gas change. As though we increase the entropy, we are going to be increasing the entropy as we are increasing the more independent movement of the particles. So in a liquid form, a lot of our particles are still close together. They are moving fluidly together. As a gas, these are now moving independently, right? There's more options, more space for the molecules. So there's more entropy in the gas phase. And so again, this is a delta S that is positive, energetically favorable. The second law of thermodynamics is important here. Remember, the first law says that energy cannot be created nor destroyed, but it can be transferred. The second law of thermodynamics says that the total entropy change of the universe must be positive for a process to be spontaneous. That idea is going to come back to us when we start to derive some of our equations here. So for a reversible process, something that can go from back and forth, something that we are going to look at again in chapter 15 later on in unit 4, delta S of the universe is 0. If delta S of the universe is less than 0, negative, that is a non-spontaneous process. If delta S is positive, greater than 0, then it is an irreversible spontaneous process, meaning yes, it will occur just as we see it in this state. If the entropy of the system is decreasing, then the entropy of the surroundings must be increasing. So notice in this equation here and in the second law of thermodynamics, we're not saying the delta S of the system has to be positive. We're saying that the delta S of the overall universe, the system plus the surroundings, must overall be positive. So we could be entropically unfavorable for our system, but favorable entropically for the surroundings. And we'll talk about how to calculate these in just a second. Right now, what we just need to be able to define is the second law of thermodynamics is specifically looking at the total entropy change of the universe. So it's not just the system that we want to look at, it's also the surroundings as well. So let's look at this situation. We have two isolated, notice the stopcock is closed, two isolated systems, I'll highlight it. One side has 4 molecules, the other side has 0 molecules, okay? When the stopcock is open, the gas atoms actually distribute themselves in a number of arrangements. These are what we call energetically equivalent states, A, B, and C over here. State A is when all the 4 gas particles stay on the left. State B is when they all move to the right-hand side. And state C is when they move half half of them to the right and half of them stay on the left. This is looking at the options. All right, it doesn't matter in terms of potential energy whether the molecules are all in one flask or evenly distributed, but one of these states is more probable than the other two. There's only one possible arrangement that gives state A and one that gives state B. All right, but really what's important to understand is the ability of state C here, okay? So notice in microstate and macrostate A, right? This is A up here on the top hand side. All 4 atoms are identical. All 4 atoms exist in the 1, 2, 3, 4 quadrant, right? There's specific points there. Same thing with state B on the bottom. 1, 2, 3, 4 atoms. And in the microstate, we can label those positions as 1, 2, 3, and 4. Here's the big kicker with microstate C. The macrostate shows 2 molecules on either side, right? Evenly distributed. But look at all of the options. Look at all of the microstates. Those 2 atoms can be on the top when the other ones are on the bottom. They could be on the left when the others are on the right. They could be diagonal and those can be diagonal. There's so many options now that the molecules have separated. So these microstates all have the same macro state. They all have the same number of particles, but there are 6 different particle arrangements that result because of this distribution. And so macrostates and probability is really what entropy is all about. State A and state B have only one possible arrangement because there's 4 atoms, they're taking up all 4 positions, all 4 quadrants, and they're set in stone. State C has 6 options. And so state C is the macrostate with the highest entropy and also has the greatest dispersal of the energy. Therefore, C has the higher entropy than A or B. And that's what we're going to try and deal with molecules. One way to see that is, are the molecules spaced out, as in gases, are more or have a higher entropy than liquids? Liquids have a higher entropy than solids. Or is it the number of particles? If we increase the number of atoms or molecules on the product side, our reaction is higher in entropy on the product side. So changes in entropy, delta S, again, is a state function. And entropy change is favorable when the result, the product, is more random. So delta S is positive. I know it's opposite of what we've been dealing with delta H. It's something we just have to remember. They're measuring 2 different things, so the sign will be different for favorability. Changes that increase in energy. Reactions whose products are more in a random state. Gases are have a higher entropy than liquids, and liquids have a higher entropy than solids. All right, solids are organized, gases are not. Reactions that have a large number of products, in terms of molecules or ions, that is entropically favorable. An increase in temperature, right? A reaction an increase in entropy results in an increase of temperature. That one's not as obvious to us. And solids dissociating into ions. I feel like this last one is the same idea as the larger number of product molecules, right? Solids are structured and their ions stick together. If we can dissociate them by making an aqueous solution, those ions dissociate, create more particles, so more product. Again, this one is a really good one to remember. Solids are lower in entropy than liquids. Liquids are lower than gases. The more degrees of freedom the molecule has, the more microstates are possible and the more macrostates are possible, so more entropy. Solids have fewer macrostates. They can't move around as much as liquids, and liquids can't move around as much as gases. Gases have the best ability to move, and so they have the most microstates and therefore the most entropy. So let's look at these real quick, these practice problems. Predicting the sign of delta S for each process, going from H2O gas to H2O liquid. This is becoming more ordered. Take a moment. Determine what that delta S would be. Take a moment and pause the video and try to see if you can come up with a sign for each of these. Again, not a number, just a sign, positive or negative. All right, first one. Going from a gas down to a liquid is becoming more ordered, so that would be delta S as negative. Solid carbon dioxide sublimes. Sublimes means that it's going from a solid to a gas, so that would be delta S that is positive. Going to a gas is always going to become higher in entropy. 2 N2O gases to make 2 N2 gases and an oxygen. This side has 2 molecules. This side has 3 molecules. They're all gases, so their state doesn't change, but because the number of particles is increasing, entropy is increasing. Same thing with D, E, and F. Pause the video, try to figure it out. All right, the boiling of water. That is H2O liquid to H2O gas. Again, going to the gas phase is always entropically favorable. Delta S is positive. I2 gas going to I2 solid. That is becoming more structured, so delta S would be negative. And calcium carbonate solid becoming calcium oxide solid and carbon dioxide gas. 2 things favorable here. We're making a gas from a solid. Super awesome. Also, 1 molecule versus 2 molecules in the product. Delta S on both of those terms should be positive.